This is the 7th lecture in the course Signals and Systems, and the lecture today shall deal with stability, unit step response and differential equations in the context of linear time invariant systems. Stability, we had already started the discussion in the earlier lecture, and what we wanted to show that h of n, the unit impulse response, or h of t, this in the DTS, discrete time systems, and h of t in CTS, continuous time systems, they are sufficient characterizations of stability or instability of a system. To see this, let's consider a discrete time system first, in which h of n is the unit impulse response. Then you know that the output y of n is given by the convolution of h of n with x of n, so it would be of the form x of n minus k hk, k equals minus infinity to plus infinity. And the stability that we are trying to investigate is the BI-BO stability, that is bounded input should lead to bounded output. Now let us see how this relationship, the convolution relationship, gives you a condition on stability of the system. Let the input be bounded by some positive value, let's say capital L. Let x of n, which could be positive or negative, be less than or equal to capital L, which is less than infinity. Then if the system is stable, y of n magnitude should also be finite. Now if this is the story, then you see from y of n equals to x of n minus k hk, from k equal to minus infinity to plus infinity, if we take mod of y of n, it could be positive or negative, we take the magnitude, then obviously this would be equal to mod of this whole quantity, and in turn this would be less than or equal to, if we take the mod inside the summation for both, then obviously it would be less than or equal to minus infinity to plus infinity mod x of n minus k mod h of k. Is this clear? We have a product x of n minus k hk. The mod of the whole summation obviously shall be less than the summation of the mod. Alright, let's see. If summation x, let's say n over n, mod of this shall be less than or equal to summation mod of x of n. Is that clear? Because x of n could be positive as well as negative, so the summation might decrease the value. Obviously this mod is less than or equal to if the mod sign is taken inside. Now it is also true that if you have two quantities, let's say x of n, y of n, and you take the mod of the product, then it must be less than or equal to the mod of this. Alright. So, well, there is a summation here. Otherwise it's not valid. It's only in the case of summation, because the product may be positive or negative. Alright. Now, what we have shown is that mod of y of n is less than or equal to summation k equal to minus infinity to infinity mod x of n minus k mod h of k. Alright. What we are trying to find out is a bound on y of n magnitude. By assumption, your x of n minus k, this mod is bounded. X of n is bounded, is less than or equal to L, less than infinity, and therefore mod of y of n must be less than equal to, if I replace this by capital L, then this summation would be further less. Yes. Can you stop the recording and see this is not working? Sorry for the interruption. The mod y of n, if I substitute mod x of n minus k less than equal to L, obviously this would be L multiplied by summation k equals minus infinity to plus infinity mod h of k. And what you want is that this quantity should be bounded. This is the magnitude of y of n, this should be bounded. In other words, you want this to be less than infinity, which means that is the summation infinity k equals minus infinity mod h of k should be less than infinity. This is therefore a condition on the stability of the system. Now what kind of a condition? Obviously this is a sufficient condition because there are many inequalities that we have utilized in the process. This is a sufficient condition, which means that if this condition is satisfied, the system shall necessarily be stable. This is a sufficient condition for stability. The question now arises, is it necessary? To see whether it is necessary or not, we apply a small trick. This condition, that is summation hk k equals minus infinity to plus infinity less than infinity, is expressed in language like this, that hk is absolutely summable. You should be acquainted with this language. hk is absolutely summable. What it simply means is that you take the absolute value of hk and sum it over all possible values of k. The summation should be bounded. Summation should be finite. That is the meaning of hk absolutely summable. Now, as I said, this is a sufficient condition for stability. What about the necessity? Is it necessary? We shall show that yes, indeed it is necessary, and for that what we prove is the following. Given this condition, k equal to minus infinity to infinity hk less than infinity, that is, we assume this condition, we show that y of n, the output y of n, may be unbounded. As I said, if I can find one counter example, that's good enough. We will show that if this condition is satisfied, then y of n may be unbounded, and for that we apply a trick. You recall that y of n is equal to summation k equals minus infinity to plus infinity, the convolution relationship, that is x of n minus k hk. This is the general convolution relationship for time invariant linear systems. Now we now search for a particular input such that y of n becomes unbounded under this condition.
Sir, but with this statement, don't we test the sufficiency of the condition?
Sufficiency has already been
It should
proved.
be infinity. That should be equal to infinity, and then we can show that it cannot be.
So, the point is that for the necessity.
Yes. I'm sorry, I made a mistake. Given this tends to infinity. Thank you for the correction.
And it should be bounded.
To show that
y
it cannot be bounded.
To show that y of n,
Cannot be bounded.
no. That's where the difference is. It's again honesty.
Bounded.
Honesty, it may be bounded, but if you can show one example that it may be unbounded, then the system is unstable. It's that difference between honesty and dishonesty. Alright, is the statement clear now? Given that this summation does not obey the bounded condition, that is, it is unbounded. You have to show that y of n may be unbounded. If you can find even one example, then the system is unstable. That is what we are going to find. That is, we are going to find a x of n such that y of n becomes unbounded. Alright? And this x of n, please try to follow this example carefully. What we have is y of n equal to summation infinity k equals minus infinity x of n minus k h of k. Now what is y of 0? Even if one output sample becomes unbounded, then the system is unstable. Then we will show that y of 0 can be unbounded. Similarly, we can take some other example also, but one counter example, as I said, is sufficient. So y of 0 is k equal to minus infinity to infinity x of minus k hk. Now let's choose an input x of n such that when x of minus k, when h of k is greater than or equal to 0, h of k can either be positive or negative. When it is greater than or equal to 0, let's say x of minus k is plus 1. Okay. When hk is positive, we choose an input x of minus k which is plus 1. On the other hand, x of minus k is minus 1 when hk is negative. Then you see, what does this summation become? Y of 0 becomes a summation of k equal to minus infinity to infinity. When h of k is positive, it's multiplied by plus 1. When h of k is negative, it's multiplied by minus 1, and therefore the product x of minus k h of k is always positive and is equal to sum is equal to the not 1, the product becomes equal to the magnitude of h of k. Isn't that right? This product, by choosing an input like this, we have assured that this product becomes simply absolute value of h of k, and therefore this is this. And by assumption, this tends to infinity, and therefore the system is unstable. In other words, the condition the condition that hk be absolutely summable is both necessary and sufficient. Alright, we proved that it is both necessary as well as sufficient. Now we can proceed in an exactly similar manner for the continuous time case. But before we go to the continuous time case, shall we take an example? Suppose y of n, let's take an example. Suppose y of n equal to x of n minus n naught. Alright, is the system stable? What is this system? It is a simple delay by how many samples? n0 samples. And therefore what is its h of n? H of n is when x is replaced by delta. Therefore h of n is delta n minus n0. And what is this summation? H of n, n from minus infinity to plus infinity, absolute value. This summation is obviously n equal to minus infinity to infinity delta of n minus n0. Should I take the absolute value of delta? Delta is positive. Alright, therefore I don't have to take absolute value. And what is this? What is this summation? 1. That's all. And therefore the system is stable. This summand exists only at n equal to n0, just for one value of n, and the value there is unity. That's why the summation is equal to 1. Therefore the system is indeed stable. Now if I take a continuous time system, the role of h of n shall now be played by h of t, and my relation is convolution of h of t with x of t is given by minus infinity to plus infinity x of t minus tau h tau d tau. in an exactly similar manner we can prove the necessity and sufficiency of the condition for stability, which is that minus infinity to infinity h of tau d tau should be less than infinity. This is the necessary and sufficient condition for stability. Instead of deriving this again and again, let me simply point out how to do this. Alright. As usual, what we do is we take x of t to be bounded. Let us say mod x of t less than equal to L. Alright, mod x of t less than equal to L for all t. Then you take the mod of y of t, and this would be less than equal to minus infinity to plus infinity L times mod h of tau d tau, and therefore mod y of t shall be bounded if h t is absolutely not summable, integrable. Alright, this is what we mean by this. Mod h of t is absolutely integrable. This is the condition. That proves the sufficiency. For necessity, you have to take an input which is plus 1 when h of t is positive, and x of t an input which is minus 1 when h of t is negative. And in an exactly similar manner, you show the necessity. Do I have to write these steps again? No. Thank you. Let's look at an example of a continuous time system which whose stability is under question. Let's say minus infinity to t x of tau d tau. Let's consider a continuous time system which to an input x of t produces an output y of t which is the integral of this. What is this system? It is simply an integrator, right? Integrator. Now, to test the stability, the first thing to do is to find out h of t. To test the stability, we have to see whether h of t is absolutely integrable or not. Now, what is h of t? You replace xt by delta t, so delta tau d tau minus infinity to plus t, I beg your pardon. What is this function?
Depends on t.
Pardon me?
Depends on t.
Depends on t. This is simply u of t. It's the integral of delta tau d tau. So it's equal to unity for all t greater than equal to 0, because delta tau occurs at tau equal to 0, and therefore this is simply u of t. We had considered this relation earlier, that u of t is the integral of delta t, and delta t is the differential coefficient of u of t. Alright, so h of t is ut dt, and therefore mod h of t dt integral from minus infinity to plus infinity, alright, is simply minus infinity to plus infinity u of tau d tau. Have we made a mistake? Is this finite? There is a small, not mistake, there is a small what should I say, source of discomfort. Why is this minus infinity?
0.
It should be 0. Okay. You can put it there, but it's redundant. It doesn't mean anything, and therefore 0 to infinity. Now, is this finite? Obviously this goes to infinity, and therefore this integrator is an unstable system. You cannot make it in the laboratory because it is an ideal integrator. What you can make in practice with an RC network or with an op-amp is a non-ideal integrator. Non-ideal integrators are possible. An ideal integrator, because it is unstable, it cannot be realized. Okay, then we consider the question of step response. We have shown that the unit impulse response h of n or the unit impulse response h of t of a continuous time system, we have shown that they are sufficient characterizations of the system. They show whether the system is invertible or not, whether it is linear or not, whether it is time invariant or not, whether it is memory or memoryless, and finally we have also seen stability. So h of n and h of t are as if the key feature of a system. Now it turns out that since delta t and u of t are very intimately related, u of t is the integral of delta t and delta t is the differential coefficient of u of t, and fact 1 is these two are intimately related. One can go from one to the other. I need this only one arrow. These two are intimately related, and fact 2 is that h of t is the response to delta t. It follows that the response to a unit step should be equally competent candidate for characterizing the system, just like h of t. If we know the response to u of t, now we shall use the symbol psi of t, psi, as the unit step response. H of t is the unit impulse response, the corresponding response to unit step is psi of t. Similarly, a unit step in the discrete time domain shall give rise to psi of n. The textbook uses some other symbol which we shall reserve for frequency in a later part of the course. So u of t leads to psi t and u of n leads to psi n. Let's consider a discrete time system first. The response to u of n is psi n, and naturally psi n should be the convolution of u of n with h of n. To an arbitrary input u of n, the output shall be equal to the convolution of u of n with h of n, which is simply the summation h of k u of n minus k. K goes from minus infinity to plus infinity. Alright, I have simply written the convolution relationship. Now you notice that u of n minus k is 0 if k exceeds n. Isn't that right? If the argument becomes negative, then it is 0, and therefore the upper limit of the summation can be replaced by n. And in this range, k equal to minus infinity to n, what is the value of this? U of n minus k? It's equal to 1. And therefore this summation simply becomes n, k equals minus infinity h of k. Is that agreed? This is the relationship between psi of n and h of n, but this is a messy relationship. Can we make it simpler? Yes, indeed we can. We have proved that psi of n is k equal to minus infinity to n h of k. Is the derivation clear? Now you notice that if I subtract from psi of n, psi of n minus n, what do I get? I simply get h of n. Isn't that right? And therefore this is a simpler relationship between the unit impulse response and the unit step response. The unit step response is simply the difference between two unit step responses, psi of n and its previous sample, psi of n minus 1. In a similar manner, we can take a continuous time system in which psi of t shall be the convolution of u of t and h of t, and therefore this is given by h of tau u of t minus tau d tau minus infinity to plus infinity. and an exactly similar argument, that is u of t minus tau is 0 if tau exceeds t. That is, if t minus tau becomes negative, the unit step function becomes equal to 0, and therefore the upper limit cannot exceed t. Upper limit you can replace by t, and in this range u of t minus tau from minus infinity to t, it is equal to 1, and therefore we get the interesting relationship, that is, we get psi of t as minus infinity to t h of tau d tau. That is, psi of t is simply the integral of h of t, exactly like u of t is the integral of delta t. Similarly, the step response, that is response to u of t, is also the integral of the response to delta of t. This is the beauty and elegance of linearity, linear systems. Or in a different manner, h of t shall be simply d psi t dt. That is, the unit impulse response is simply the differential coefficient of the unit step response. You recall also the discrete time relationship, that is, h of n is psi of n minus psi of n minus n. Do you see the analogy between these two relationships? You see, h of t is d psi t dt, that is, increment in psi divided by the increment in the argument. Now, in the discrete time case, the minimum value of the increment in the argument is 1, and therefore what you do is you take the increment, the minimum increment in psi, which shall be one sample difference, that is psi n minus 1, this divided by the increment in the argument, which is 1. Alright, therefore the two relationships are qualitatively, at least qualitatively, they are absolutely analogous, and we say h of n is a difference and h of t is a differential coefficient. That's the only difference in nomenclature. The nomenclature here is simpler because the minimum difference is 1, unity, and we do not have to show division by unity specifically. Next, let us consider continuous time systems which are described by differential equations. And these are constant coefficient differential equations. In the later part of the class, we shall be very closely concerned with differential equations and difference equations, and I wish to review with you a bit of differential equations. I assume that you know most of it, and for that purpose we take a very simple example. We take a system which is described by a differential equation like this: y dot plus some constant 2y equal to x. Of course, they are functions of t. This means, what kind of a system is this? Is it a dynamic system or a static system? Is it a dynamic system or a static system? Whenever d dt is involved or differencing is involved in the discrete time system, it is a dynamic system. A capacitor, for example, is a dynamic element. An inductor is a dynamic element because both of them have memory. So this is a dynamic system. Consider a linear, well, we don't know whether it is linear or not yet. Consider a system which is described by a differential equation like this, which means that if an input x of t is given to it, it will produce an output y of t, such that y of t and x of t are connected by a differential equation like this. Now, to be specific, let's consider a specific input. Let's say x of t is some k, a sinusoidal input, k cosine omega 0 t, please follow this carefully, I'll go real slow on this because there are very involved concepts, times u of t. That is, we have an input x of t which is 0 for t less than 0, and it varies cosinusoidally after t equal to 0. At t equal to 0, the value is k. We wish to find out the response of the system described by this differential equation. And you know that solution of a differential equation consists of two parts: the solution to the particular excitation or particular x of t, which we shall call ypt, it is called the particular solution or particular integral as it is called, plus the solution to the homogeneous part of the equation yh of t, where yh of t is obtained by rewriting the equation with x of t equal to 0. Alright. Now let's see, let's first find out what my particular integral shall be. You see, my x of t is k cosine of omega 0 t, and we can find the particular integral obviously shall be 0 for t less than 0. Alright, okay. So we will assume that u of t is implied, multiplication by u of t. We will not write it again and again. Alright. Now this can be written as real part of k e to the j omega 0 t. You see, we have brought in that elementary signal, that exponential elementary signal, with the exponent as purely imaginary, j omega 0 t. If that is so, then obviously the particular integral ypt must also be of the same form. The particular solution is of the same form as the given excitation. In other words, it would be of the form real part of some constant, let's say a, or shall we call it y, some constant capital Y times e to the power j omega 0 t. If you substitute this in this equation and forget about the real part, that is, assume x equal to k e to the j omega t, k e to the j omega t, and assume ypt as capital Y e to the j omega t. Finally, we shall take the real part. Alright. So, what we get is, if I differentiate, then I get j omega naught y e to the j omega naught t plus twice capital Y e to the j omega naught t. If I substitute this and this in this equation, which gives me capital Y as equal to k divided by j omega naught plus 2. Alright, you have done this in Principles of Electrical Engineering, but I am doing this again not only to review but also to bring out some other concepts. Why is this? I can write this as a magnitude to the j theta, magnitude and angle, and if you take the magnitude, obviously this would be square root of 4 plus omega naught squared, and the angle shall be minus tan inverse, yes, omega naught divided by 2, or is it 2 by omega naught? So omega divided by 2. Right. So this is y, and you see my particular solution ypt was the real part of y e to the j omega naught t, and I found a y, and this is simply given by k divided by square root of 4 plus omega naught squared y to the real part, the cosine of omega t. Shall we put sign just for convenience? Alright, y e to the minus k. It doesn't matter, I could have used it also.